Gives me great pleasure to introduce Professor Shanhui Fan, who is also the director. He's a professor of electrical engineering and a professor of applied physics by courtesy at Stanford. He's also the director of the Edward L. Grinson Laboratory at Stanford, which is known for a several path-breaking experimental work that has come out of Stanford. Shanhui received his PhD from MIT in '97, working with John Johnopoulos. And in fact, I can take the liberty to say that defined the field of photonic crystals. Although the discovery had happened earlier, but really everything that we hear about photonic crystals really jump-started with his PhD work and a textbook he wrote probably while as a graduate student, which is now the defining textbook in photonic crystals. He's worked in numerous areas, but clearly one of the a real force in nanophotonics. He has done work in everything from photonic crystals to things that you will hear today of synthetic dimensions, and also even things that are practical. So he even has an entrepreneurial instinct in him. He has a company that spun off I'm not sure how many companies, but it's on radiative cooling, where you can cool apartments without actually having a cooling system where you coat it with certain materials and so on. And so they have a startup on that. He's won numerous awards. I'm not going to reel out all the awards. He's a fellow of APS, OSA, IEEE. He's been noted as a Thomson Reuters highly cited researcher in physics since 2015 for every year. And he is also the Vannevar Bush Faculty Fellow in 2017, and also won the Adolph Lom Medal from the OSA. So several awards, and I think we're in for a treat today for this new topic of synthetic dimensions. And thank you, Shanhui, for accepting our invitation, and looking forward to having you give this talk for us. And wish it was in person, but we'll do the best.
Well, thank you for the very kind introduction, Vino, and it's a pleasure for me to come here. I certainly have quite a few friends in here. As advertised, I'm going to be talking about synthetic dimensions in photonics. So here's a brief outline. I would start by discussing a bit of a theory to provide both the background as well as some of the more recent theoretical development. Then I'm going to talk about experiments, and both the theory and experiment concerns topological physics. And then towards the end of my talk, I'm going to talk about I think, an interesting new direction in thinking about synthetic dimension, and that is to try to do optical computing in synthetic dimension. So as way of motivation, certainly physics depends very significantly on the dimensionality where the effects take place. And this is in particular true for topological physics. There are many topological physics effects that only happen in high dimension and have no low dimensional counterpart. As two prominent examples that have been widely studied, the wild point physics, which start at 3 dimensions, as well as the generalization of quantum Hall effect into 4 dimensions, which give rise to a different class of topological invariants. So the concept of synthetic dimension is developed to try to explore these kind of higher dimensional physics in lower dimensional physical systems. Certainly, we live only with 3-dimensional space. So if you are interested in exploring 4-dimensional spatial physics, you are out of luck, at least by ordinary means. Also, many of the 3-dimensional physics, it will certainly be interesting to be able to explore them in 2-dimensional structures that are easier to fabricate and to explore. So the concept of synthetic dimension is actually a very natural one. As an illustration, suppose you were given the task of representing the 3-dimensional physics of an array of cylinders with varying heights with a 2-dimensional representation. Now, the natural thing that anyone would do is to draw a 2-dimensional array of circles and then represent the height of each of these cylinders by color. So in doing so, in fact, in the language of synthetic dimension, this is to take a two-dimensional spatial lattice and add one synthetic dimension. And in this case, is the dimension of frequency. And you use that to explore three-dimensional physics. So this idea has been around for a long time. It certainly has been extensively explored in condensed matter physics, in atomic physics, and more recently in some of the experiments on superconducting qubits. What I hope to convey here is that it's also a very interesting concept in photonics. And in fact, a couple of years ago, we wrote a fairly comprehensive review highlighting some of the opportunities that synthetic dimension correspond to in photonic science and engineering. So there are many opportunities in photonics to pursue the synthetic dimension concept. Here, I just like to focus on one particular avenue, and this is to take a single optical ring resonator. In the absence of group velocity dispersion in the waveguide, the light will go around, and the periodic boundary condition then indicates that the eigenfrequencies are quantized. So the ring will support a set of resonances with equally spaced resonant frequencies. And the frequency spacing here is reciprocal to the round trip time. Starting from this, if one then put in a phase modulator for which the transmission coefficient is dependent harmonically as a function of time, and moreover, if one chooses the modulation frequency to be equal to the free spectral range or the mode spacing, then the modulation is going to resonantly couple different modes together. Consequently, the modulated ring is described by a tight binding model of this form, where each lattice side of the tight binding model corresponds to a mode at a specific frequency, and then the modulation couple these different frequency modes together. So in this case, we start with a ring or single cavity, which can be thought of almost as a zero-dimensional object, and we endow it along the frequency axis a one-dimensional physics. And that's the synthetic dimension argument. Moreover, the phase of the modulation in fact translate into the hopping phase of the nearest neighbor frequency modes. So consequently, the phase of the modulation, in fact, is a gauge potential for light. So one can use this gauge potential to break reciprocity or time reversal symmetry and to generate effective magnetic field. And that provides a lot of flexibility in exploring different kinds of topological physics. So as an example of this, one can consider a one-dimensional array of rings, and within each of the ring, one put in a phase modulator, and then one control the phase modulation phase distribution in space. For this system, it actually corresponds to a two-dimensional lattice. As I mentioned, each modulated ring can be described by a tight binding model along the frequency axis. Moreover, near a given resonant frequency of a ring, the modes can tunnel from one ring to the next by evanescent tunneling. And that gives rise to a one-dimensional lattice along the frequency axis. Combine these two, therefore, this system, which is a one-dimensional array of resonator, in fact, it can be described in a two-dimensional square lattice. Now, if I choose the modulation phase of this modulator according to this particular spatial field distribution, then this in fact corresponds to the Landau gauge of a uniform magnetic field perpendicular to the plane of these two-dimensional lattice. Consequently, this lattice actually supports quantum Hall effect for light. It support one-way edge state that are topologically protected. So if this lattice is finite, then it support one-way edge state that go around the edge of the synthetic space as defined by frequency and space. This is like the regular one-way edge state that you see in two-dimensional lattice under magnetic field. But the interesting aspect is that part of the propagation is on frequency space. So if you excite this ring, which is on the edge, at a particular resonant frequency, then as time evolves, the frequency will first upshift until it hits the frequency boundary. And then it's going to propagate across the ring array. And then on the other side, the frequency is going to downshift. So this, as I mentioned, look like a regular one-way edge state, but the propagation can occur in frequency. And that gives you a way to control frequency of light in a robust way. So I've shown you a simple example of implementing two-dimensional quantum Hall effect. There are, in fact, a large number of non-trivial topological phenomena that can be explored in this way. And these are some examples that we have considered, ranging from, these are all photonic implementation, but ranging from wild semi-metal to a three-dimensional topological insulator, to higher order topological insulator that I'm going to try to focus on today, just as an illustration of some of the theoretical possibilities. So conventional or first order topological insulator, in these systems, if it's a d-dimensional gap bulk, you will have d-1 dimensional gapless boundary states. So for example, a 2D topological insulator, including the one that I talked about, support a one-dimensional chiral edge state, and a three-dimensional topological insulator support a two-dimensional surface states. As a generalization of the topological insulator concept, there are these higher order topological insulator where a d-dimensional gap bulk support a d-n dimensional gapless boundary states. And this is referred to as the nth order higher order topological insulator. So for example, a second order topological insulator or the quadrupolar topological insulator is a system where you have a two-dimensional lattice, but it support a topologically robust corner states. Similarly, the third order topological insulator has a three-dimensional lattice that support a zero-dimensional corner states. This class of high order topological insulator has been proposed a few years ago and have generated substantial interest, especially in photonics and phononics community. So these are some of the initial demonstration in the photonics and phononics side. And also, I would like to mention the pioneering work of people here, Professor Hanikave, Alex Hanikave, and Andre Alou on demonstrating this for acoustic wave. Now, if you look at the structure that has been demonstrated, these are largely restricted to a two-dimensional system. So, and also typically involve very sophisticated geometry, that some of them fabricated by nanolithography. So it certainly will be interesting to figure out a way to explore these high order topological insulator in higher dimensions. And moreover, it would be interesting to provide simpler experimental demonstration implementation, and also providing more tunability and reconfigurability. And that naturally lead to the consideration of implementing these kind of concepts in the synthetic dimension, in the synthetic space. At the heart of these high order topological insulator proposal is the SSH model, the Su-Strifer-Heeger model, which is the perhaps the simplest topologically non-trivial model that occur in one dimension. So in the SSH model, is a one-dimensional tie-binding model with a nearest neighbor coupling. In this model, each primitive unit cell contains two atoms or two lattice sites, and the strength of intracell coupling to the intercell coupling, the two strengths are different. And when they're different, the system actually has a non-trivial topology as protected by mirror symmetry. So, and it will support a topologically non-trivial or topologically protected edge state exactly at the center of the gap. Now, the higher order topological insulator in many ways can be thought of as a higher dimensional generalization of the SSH model. So I will first like to talk about how to implement this in synthetic dimension. And to do so, you take two rings. And you can assume these two rings to be the same. In the absence of modulation and coupling, then each of the ring will support a frequency cone or a lattice of frequency modes. And also at every frequency, the modes can be, every resonant frequency, the mode can be either in ring A or the ring B, and they're degenerate. Now, suppose you allow evanescent tunneling between these two rings as described by a coupling constant K. This is going to split these otherwise degenerate mode into an even and odd mode with a frequency spacing. So consequently, along the frequency axis, one have now a array of modes with unequal spacing. And so each primitive unit cell in this lattice, therefore, have two lattice sides. And to couple all these modes together, we then modulate the ring with a modulation frequencies correspond to these two different frequency spacings. Importantly, because these two modes in each unit cell, in fact, has different spatial parity, one of them is even, the other one is odd when you couple the two modes together. In order to dynamically couple these modes with different parity together, the modulation need to have a dipolar profile. The phase of the modulation on ring A has to be 180 degree out of phase from the phase of the modulation on ring B. So that then gives you an SSH model with two modulated rings. Starting from this, you can construct a quadrupolar topological insulator. So what you do is you make a one-dimensional array of these double ring structure. And in this case, one choose the spacing of this array so that along the spatial axis, the system also look like an SSH model. And so in doing so, each of the double ring has a frequency axis described by a SSH model, and then along the horizontal axis is also SSH model. Moreover, to have quadrupolar topological insulator, some of these plaquettes need to be threaded with a pi magnetic flux. And this is done by controlling the phase of the modulation. For example, within each unit cell, one use a quadrupolar phase distribution in modulation. This then gives you a construction of a quadrupolar topological insulator. Here is the calculation of the eigenenergy as a function of the ratio between these two tunneling rates. And we have chosen the two modulation strengths to be sufficiently different such that in the presence of this quadrupolar modulation phase distribution, if the tunneling rate between the two is sufficiently different, the system is actually in this quadrupolar topological insulator phase. And when you look at the eigenstate of a finite size lattice, it has bulk modes, edge mode, as well as a corner state that the frequency of which is independent of the ratio between the two. And that gives you some sense of the topological robustness of this corner state. And one can selectively excite these states both by selectively exciting some of the rings, so it's a selective excitation along the real space, as well as in the frequency space by choosing the excitation frequency. In choosing an excitation frequency, one can choose it to be near a particular resonant frequency that provide an excitation of selective excitation of that particular lattice site along the frequency axis. And then the small detuning allow you to probe the Floquet band structure. So for excite a corner mode, for example, one excite the rings on the left edge and also choose the excitation frequency to be close to where the corner mode is in the frequency axis. And you can do that for the edge modes and the bulk modes as well. So when you do that, and if you plot the energy that is in the leftmost ring here where you excite, you can see that in the topological regime, one can see a clear excitation of the corner mode, which now is absent actually in the trivial regime. And here are some of the field distribution associated with these excitation scenario. So in this case, we excite the leftmost ring near the resonant frequency at the boundary, and one excite a corner mode. In this case, we excite the edge mode by again focusing on the leftmost ring, but choose the excitation frequency that correspond to a lattice site and also the right detuning for the edge mode. And in this case, you can see that the field distribution indeed is concentrated on the edge. To excite a bulk mode, we can choose the excitation to be on some of the rings in the center of the array. And again, the appropriate choice of the excitation frequency, and then the field distribution now occupies the bulk. So one could actually selectively probe different kind of mode in the system by choosing different ring to excite and by choosing different frequencies. One interesting aspect of the synthetic dimension idea is that it allows you to naturally create topological phase transition. So in as we have mentioned, this quadrupolar phase distribution in the modulation is very important in generating the non-trivial topological phase. So if you have a quadrupolar phase distribution, meaning that the modulation on these two rings are 180 degrees out of phase with the modulation on these two rings, then you create a non-trivial bulk band gap supporting a corner mode. And this corner mode persists even after you introduce substantial disorder. You can see that this is how the corner mode look like in the presence of disorder. On the other hand, if you don't do a quadrupolar phase distribution in the modulation, for example, if you modulate these two pair of rings in a unit cell in phase, then the system, in fact, is just a two-dimensional SSH model. In this case, the band gap, in fact, becomes trivial, and the system do support edge modes, but these modes are not topologically robust. If you put in disorder, then even if you excite at the corner, the field is going to penetrate into the bulk region. Now,
hi Shanhui, can I ask
yes.
you a question?
Yeah.
Maybe related to this, but in photonic system, what is being synthesized is this vector potential, right? Generally, you kind of engineer the right vector potential so that it gives you some constant magnetic field.
Right.
And so, but when you think about the disorder in this system, so the disorder will be in the implementation of the vector potential.
No, so the disorder, well, you could certainly implement a disorder in vector potential. You can do that.
No, but if let's say if there are experimental errors that are happening in this implementation,
right?
It will certainly have some fluctuation in this.
So in photonics, the dominant disorder usually come from fabrication inaccuracy. So for example, in the fluctuation of the resonant frequencies, the vector potential, the modulation phase, which, as I mentioned, give rise to the vector potential, those are controlled electronically. Those are controlled in a modulator. In fact, I'm going to show some experiment where this probably will come up even more transparently. Those are microwave signal generated by a computer in essence. And so those can be computed to very high accuracy. So in fact, of course, you could do this order in vector potential, but most likely the natural disorders are the resonant frequency and the coupling constant fluctuation.
Yeah, so one of the things is that, okay, if you can control vector potential very precisely, then, but in some sense, you are kind of gauge fixing your system, right, by picking the vector potential. So, in principle, you are losing gauge invariance of your system by actually.
No. So in this case, gauge fixing doesn't enter. Maybe I can go back one slide. Let me want to make sure that if you look at this, then this is just a gauge degree of freedom. This is the modulation phase.
Right.
And so this actually by itself doesn't have measurable effect. But if you have two of these, which is what we show here, the phase difference is a gauge invariant quantity. And that is in the end correspond to the magnetic field, which are the gauge invariant quantity. So you can do that with any gauge you choose to. In other words, the gauge, in fact, correspond to the arbitrariness of the modulation phase at a one modulator, but the modulation phase difference is gauge invariant.
Right. Okay. Okay. Thanks.
Yeah. Thanks for asking. Feel free to interrupt me. Okay. So let me come back. So as I mentioned, that in this case, now the transition between the topological quadrupolar topological insulator phase and the 2D SSH phase, which is topologically trivial, in fact can be done, as I just mentioned, to Sriram by changing the modulation phase distribution. So this is something experimentally, in fact, that can be straightforwardly done with electronic means. So lastly, very quickly, one could in fact implement third and fourth order high order topological insulator in these systems. So I won't go into too much of a detail, but the three-dimensional third order topological insulator can be done with a two-dimensional array of rings suitably constructed and with modulator put in. And the fourth order one is then the stacking of these rings in the third dimension. So in fact, this point to really the possibility, as I hope to illustrate, that one could do some of the high dimensional physics in a slightly more simpler way than directly fabricate, for example, complicated structures in 3 dimensions. So that concludes the theory part of on these synthetic dimension. And in the second part of my talk, I like to talk a bit about some of our experimental efforts. And so as a starting point of the experimental effort, much of the topological material research concerns the characterization, both theoretical and experimentally, of non-trivial topology in band structure. So in this regard, therefore, it will be very important to actually to be able to measure the band structure. And so the first thing I'd like to show you is how one can measure the band structure experimentally in synthetic space. As I mentioned, if you have a ring and if you put in a phase modulator with the modulation frequency equal to the frequency spacing between the modes, this is a tie binding model along the frequency axis and is a periodic system. And therefore, you can plot energy as a function of wave vector, and it gives you the usual cosine looking tie binding band that you have, of course, all learned in your introductory solid state class. Now, for synthetic dimension, frequency or energy, of course, you know what it is. The slightly more subtle aspect is what a wave vector is. So given that our coordinate here is frequency, the wave vector along the frequency axis need to be conjugate to frequency. And therefore, the variables is in fact time. So in fact, by measuring time-dependent property of the system, one can measure the band structure in synthetic space. And more specifically, suppose you imagine experimental setup. This is the modulated ring, and this is the waveguide carry the incoming excitation, and you choose the frequency of the excitation. And then you look at the transmission of light in the outgoing waveguide as a function of time. Given that you are modulating the system, naturally you should expect that the transmission will vary as a function of time. On the other hand, the time here is a wave vector. So therefore, what you what you are looking at, in fact, is a transmission as a function of frequency and wave vector. And we know that in these kind of transmission, you will expect high transmission or high resonant response when the frequency and the wave vector matches with one of the mode in the system. So that then provides you a way to measure the band structure. So in fact, this is the theoretical calculation. At each frequency, we measure the transmission as a function of time, and then we put them together in a two-dimensional diagram, and you can see that a cosine looking band naturally emerge in these kind of calculation. So we then build an experiment to demonstrate this. So in experiment, we use a fiber loop of a length of 13 meters with a free spectral range of 15 megahertz. And we use a laser to probe this. So we use a laser with very narrow line width so that we can probe frequency scale significantly below the free spectral range. And also, this laser allows the frequency to be varied so that we can measure the system at small detuning from the resonant frequencies. For the modulator, we use a lithium niobate electro-optic modulator, which can modulate up to 2 gigahertz. And this is significantly larger than the free spectral range of the ring. And that allows us, therefore, to modulate at multiples of the free spectral range. The modulator naturally has loss, but for fiber device, one can naturally compensate it back with a semiconductor optical amplifier. So the system can be operating essentially at a lossless limit. Lastly, in the detection, we use a fast photodetector. This is a 5 gigahertz photodiode. This frequency is much smaller than the much larger than the free spectral range. So we have the time resolution to probe at a time scale that's much smaller than the round trip time of the photon in the system. So putting this together, what I'm going to show you is an experimental measurement where we vary the frequency of the input laser. And for each of the frequency, we then record the transmission as a function of time. So the movie here shows you the process. As we scan the frequency, we record the transmission as a function of time. And you can see that the transmission exhibit peaks as a function at various times. And if you take the experimental data, as we show here in the movie, and collect them into a two-dimensional plot, this is what we see experimentally. And you indeed see very nicely the cosine band coming out. And in this case, in a tie binding model, the strength of the nearest neighbor coupling controls the bandwidth of the band. In our case, the bandwidth here, or the strength of the coupling, is controlled by modulation strength. So if you increase the modulation strength, you can see experimentally that the bandwidth of these bands indeed increases. And moreover, this is constructed by a time-resolved measurement. You can also do a time average measurement by looking at the transmission as a function of frequency average over the modulation period. When you do that, The blue curve example is the measured transmission spectrum. And this, in fact, theoretically, is measuring the density of state of the bands. And experimentally, you see that the Van Hope singularity at the band edge, for example, shows up very nicely in these kind of measurements. Now, as a last point, and I think it's a recurring point I like to make, in synthetic dimension is very straightforward to reconfigure the system. So in this example, you can add in a 2 omega component in the modulation, and that corresponds to next nearest neighbor coupling. And so the tie binding model look like this, or you can plot them in a slightly more readable way. So the solid line here corresponds to nearest neighbor coupling, and the dashed line here corresponds to second nearest neighbor coupling. The phase difference between the omega and the 2 omega component then translate into a magnetic flux threaded in these triangular plaquette. If this phase is different from 0 or pi, then the Hamiltonian break time reversal symmetry, and the band structure is asymmetric around K. And this is what we see experimentally. Again, I show you a movie. So again, the same thing. We scan the frequency, and for each frequency, we record the transmission as a function of time. We collect the data to form this diagram, and you can see a very nice asymmetric band structure with respect to 0. And as I mentioned to Sriram just now, controlling modulation phase difference is a straightforward thing in electronics, and you can just do it by turning a single knob. And if this phase is pi over 2, as I mentioned, you have a non-reciprocal band structure that break time reversal. If this is pi, the system has time reversal symmetry, and the band structure becomes symmetric. So with the capabilities demonstrated for measuring band structure, what I like to do next is show you a demonstration of quantum Hall effect for photons. So this is a canonical way to present quantum Hall effect. You have a square lattice, you apply a magnetic field, and with the right magnetic flux per unit cell, the system will open non-trivial topological band gap. And if you have a stripe, then at the edge of the stripe, there are edge modes. And these are at a given frequency, you have a left going and right going, or in this case, go upward going and downward going modes, but they localize on different edges. And so these are the chiral edge state. So for example, this mode here, which is concentrated on the left edge, is going only downward. And this mode here, which going upward, is concentrated on the right edge. So these are the standard chiral edge behavior in quantum Hall system. Now, one of the interesting aspects is if you can start with the quantum Hall system, but remove all the bulk. If you do that, you get a quantum Hall ladder because the only thing you have is the edge. Since you remove the bulk, you should expect that all the bulk bands will disappear. However, remarkably, in this Hall ladder system, where you only have 2 lattice sides in the horizontal direction, the resulting state, the edge state, actually remains. So in fact, the eigenstate of this Hall ladder, the dispersion relation look almost exactly the same as the edge state of a quantum Hall system. So again, you have one of the state going in one direction, concentrated on the left edge, the other state concentrated on the right edge and going in the opposite direction. So the chiral edge state survive in this Hall ladder. So in this sense, the Hall ladder is probably the minimum system that is required to see one-way edge state.
Shanhui, I have a question here.
Yeah, go ahead.
Generally, this Hall ladder has a problem that any backscattering can kill the topology, right? So you're somehow using some engineering to prevent that from happening.
In principle, of course, because there's no bulk protection, you will have a scattering from one to the other. However, they still are, the scattering is expected to still be suppressed somewhat because there's still an energy localization on the two edges. So the overlap of them is still relatively small. But I agree with you that bulk is important for a strong protection against the disorder.
But what I'm saying is that it seems that you don't even need topology. Your sheer engineering of this, the quality of engineering of the system will get you the kind of one of the more interesting properties of a topological system, which is like one-way propagation. So in some sense, you are creating a fiber which has such high quality that there will be literally no backscattering, and you don't even need topology to protect that.
I think that's a reasonable point. Certainly, I would say I will agree with you that it's hard to argue for topology strictly in this system. But what I would like to say rather is that it's a remnant of the topology of the bulk in these Hall ladder system. It's an extreme case where you essentially get rid of the bulk, but some of the effect that we commonly associated with the bulk topology still stays, is probably how I would say it. Certainly, given that there's no bulk, defining a Chern number for the bulk would have been somewhat dubious for the Hall ladder.
Because in the sense that one of the defining features of topology is that it should be robust against any small perturbations, right?
Right.
And if you actually introduce any perturbation, this will just go away. And but it seems that you're compensating for that by some high quality device engineering, which kind of almost makes this perturbation zero.
That's one part of it. But I said because of the localization of the state on the two edges, there's still some protection of the disorder scattering compared with a regular waveguide with the where the forward and backward mode perfectly overlap in space. If you compare those two, then this system is more robust in the sense that for the same perturbation strength, the backscattering is weaker. But of course, it's not zero, or it's not asymptotically zero.
Yeah, so just one more point that let's say if you have a simple Luttinger liquid-like system or a simple 1D wire, which with two channels, like one going forward and one going backward. Let's say if I can create an ultra clean wires like that with only two counter propagating channels. So that will be almost like your ladder system, right?
Well, not quite, because in this case, you still have two channels, spatial channel. And the forward going mode and the backward going mode occupies the two different channels. So it's different from a single channel where you have forward and backward mode, but the spatial modes are perfectly overlapping. The strength of the backscattering in those two cases are different.
Yeah, so but let's say hypothetically, I can completely clean up that wire. Let's say
if you clean up wire, then there's no backscattering. But my point is that the two systems are qualitatively different.
Okay. So I think Vinod has a question. Vinod, go ahead.
So Shanhui, in these Hall ladder systems, what happens if I remove one of the lattice sites? On say instead of say you have the upward propagating on the left edge, but I remove something off the right edge. In that system, what happens in that case?
So any disorder would give you a little bit of backscattering, but keep in mind that the only way backscattering can occur is for it to go from, for example, the left edge to the right edge.
Yes.
So it will do that, but the strength of it will be smaller compared with in a regular system where the two modes overlap perfectly. So good. So let me move on. So as I mentioned, this Hall ladder system really has been extensively looked at experimentally in atomic physics, but all the implementation up to now have used at least one real space. So what we provide is perhaps the first demonstration of this Hall ladder in photonics but also the first demonstration of the entirely using synthetic dimension concept. So what we do is we take a ring. A ring has a clockwise rotating state, so waves that going this way, and a counterclockwise rotating state, the wave going in the backward direction. And so, as I mentioned, each of them forms a frequency lattice. So now we have the two legs of the ladder. And we put in an electro-optic modulator so that we connect the coupling along the frequency dimension. And to construct the rung of the ladder, we need to couple the clockwise, the counterclockwise modes. And this is done in a control way by putting a figure 8 coupler. So with a figure 8 coupler, for example, if you have a clockwise state, it come in and goes through the blue arm of the coupler and come out as a counterclockwise state. Similarly, if you have a counterclockwise state, it go in along this purple arm or pink arm of the coupler and come out as a clockwise state. So therefore, the figure 8 coupler create this horizontal coupling for modes at the same frequency. Now, we choose the length of the blue and the pink arm to be different so that the coupling from clockwise to counterclockwise acquire a phase that's different from the coupling from counterclockwise to clockwise state. And that phase is proportional to the difference in the length of these two arms, but also proportional to frequency. And therefore, for each of these rungs, in fact, the direction-dependent phase is different. And that then implements a magnetic field perpendicular to the Hall ladder. In our experiment, I mentioned that we can do band structure measurement, and moreover, we can do spin resolved band structure measurement. So if we excite and detect clockwise state by sending light from the left, we can also excite and detect counterclockwise state by sending light from the right. So therefore, we can measure band structure projected onto the two quote-unquote spin, and these are the clock and counterclockwise modes. So if you do a theoretical calculation, this is the band structure, but projected onto the clockwise state, and so projected onto one leg of the ladder. And you can see this one-way feature concentrated on one leg. And if you project on the counterclockwise state, you see it's now concentrated in a different propagation direction. And this is indeed what we observe experimentally. If you project onto the clockwise state, you see half of the band structure. And if you project onto the counterclockwise state, you see the other half of the band structure. Again, we can control the band structure in great detail by changing, for example, the modulation strength. We can go from a band structure where the minimum is k equal to 0 to a band structure where the minimum is away from k equal to 0. In condensed matter, this is often referred to as the phase transition between the Meissner phase and a vortex phase. In photonics, we don't have the same physical meaning of such a minimum in k space, but I'm borrowing these terminology is simply to highlight the capability of band structure control. Lastly, about the experiment, one can also measure the chiral current. So as I mentioned, for example, on the clockwise side, on the left side, the one-way state is going downward. So if you excite at a particular frequency, the frequency that you are generated would be mostly lower than the excitation frequency. Whereas if you excite the lower band at the same leg, the frequency goes upward. And in this case, you have mostly upshift of frequency. And so to demonstrate this, we would need to measure the frequency component of the light that's being generated. And so what we do is we define a chiral current, and this is if I send in at a particular excitation frequency, how much of it come up above and how much of it come up below in terms of frequency. And these frequency can be measured in a heterodyne detection scheme. If I take a incident excitation frequency, I can get part of it through an acoustic optic modulator to move the frequency a little bit. And then I beat this with the output of the ring. In this case, it would generate a time fluctuating intensity. And by Fourier transform the time fluctuating intensity, I will get a peak in the microwave frequency range. And the position of the peak measures the amplitude, the height of the peak measures the amplitude of the frequency component in one of the sideband in the optical frequency range. So with this technique, you can plot out the chiral current as a function of detuning, and exactly as expected, for clockwise band, for example, the chiral current changes sign because the groove velocity here changes sign. And if you pick one of the detuning, you can clearly see that the frequency really mostly move up rather than down, and that gives you the one-way edge state signature. And if you flip the sign of the magnetic field, the direction of the frequency translation also flip sign. And the sign of the magnetic field can be straightforwardly flipped by simply flipping the physical orientation of the figure A coupler. So up to this point, I have talking mostly about the application of the synthetic dimension concept as a way to demonstrate interesting topological physics effect. In the last maybe 3-4 minutes or so, I would like to switch gear and talk about our recent effort in trying to do these synthetic dimension in the context of optical computing. So in fact, there has been a lot of interest recently to use optics to do matrix vector multiplication. As a simple example, if you have a Mach-Zehnder interferometer array, you send in a input vector in terms of the amplitudes of the wave at each of the single mode input waveguide. Then upon transmission, you generate the output magnitude, output amplitude, that is a linear transformation of the input amplitude. So you do, in essence, a matrix vector multiplication. And it has been pointed out that arbitrary unitary vector, in fact, can be generated this way. Now, this is interesting because, in part, because of the interest in developing optical neural network, where one can use this kind of setup to significantly speed up the calculation of matrix vector multiplication, which dominant in the computational cost of neural network. Also, in this particular implementation, given a matrix, generally the degree of freedom scale as n squared, where n is the dimension of the matrix, one would need n squared controlling knob, and this in terms of n squared modulators. So instead of doing this in the spatial mode, as I showed here with the Mach-Zehnder interferometer mesh, what we recently explored is the possibility to achieve arbitrary frequency mode conversion. So in this case, what we envision is a device that you send in an arbitrary spectrum of a discrete set of frequency component. It would generate for those frequency component another arbitrary spectrum that is linear transformation of the incoming spectrum in terms of complex amplitude. And this is done by using electro-optic modulator and by choosing a non-sinusoidal modulation profile that is nevertheless periodic, and therefore it has multiple modulation tone, and by controlling the strengths of different modulation tone. And this is interesting both in terms of a way to control the frequency content of photon, but also has interesting implication for trying to implement optical neural network in synthetic dimension as well. So in order to do this, one of the first things that one would like to do is to ensure that we are living in a finite dimensional frequency space so that the frequency component does not leak. If you take a ring and put in a, take a ring and without modulation, you look at the transmission spectrum, you can see a periodic array of resonances. If you put in a modulator with a modulation frequency equal to the spacing between these dips, then you will go do frequency translation or frequency generation and multiple of the modulation frequencies, but it will go very, very far in the frequency space. And this, in essence, provide a leakage along the frequency axis. So if we like to do a unitary frequency, arbitrary frequency conversion, we need to be able to truncate the frequency axis. And this is done by introducing another ring, usually smaller, so that its free spectral range is the multiple of the big ring. And in doing so, these two rings would be on resonance periodically along the frequency axis. When they are on resonance, they couple, and that split the resonant frequency so that the modulation can no longer couple these modes together. And as you see here, if we introduce this extra ring, again, look at the output spectrum in the presence of electro-optic modulator, now it's concentrated only within a small number of frequency components. From this, one can then design the modulator to construct a arbitrary n by n scattering matrix. Now, the degree of freedom in a unitary scattering matrix is n squared. In what we do, the degree of freedom in the device is the modulator. Then each modulator can have n to sub m of modulation tones. And for each of the tone, one can have the amplitude and the phase of the modulation. So the degree of freedom is the number of rings times the number of modulation tones and times 2 accounting for the amplitude and the phase. So what we do is we use inverse design to adjust this modulation degree of freedom until we can get a particular scattering matrix. But given that the scattering matrix has a particular number of degree of freedom, one expects that the inverse design will be successful only if the device have enough degree of freedom to satisfy the degree of freedom in the scattering matrix. And this is indeed what we see in the numerical simulation. So as an example, consider a 5x5 matrix we're trying to implement. And in this case, this is essentially a circulator in the frequency space. So if you send in frequency 5, you get 3. And if you send in 3, you get 1, and so on. And a 5x5 matrix has 25 degree of freedom. So if we choose 4 ring with 4 modulation tone, it will have 32 degree of freedom. And we run inverse design, we can indeed get something that's very, very close to this target. In general, we can define a fidelity in terms of the target matrix and the resulting matrix. And we can look at the best fidelity that we can get as we change the degree of freedom. And what we see in this graph is that if the number of degree of freedom is small, no matter how you design it, it's in fact difficult to approximate the matrix that you care about. But once you have enough degree of freedom, then it is actually possible to approach arbitrary matrix with very, very high accuracy. So as I mentioned, in doing so, we move the matrix vector multiplication from spatial to spectral domain. In this case, because part of the degree of freedom is in the modulation tones, this significantly reduces the number of modulator that is required. And we are actually quite interested in thinking of this platform as a stepping stone towards demonstrating neural network in the synthetic dimension, as well as performing some of the quantum computation in synthetic dimension. So with that, let me summarize. I guess I hope to convey that there are really a lot of interesting things that you can do in the synthetic dimension concept, both in terms of fundamental physics, in terms of, in particular, topological physics, but also potentially in some of the application involving, for example, manipulating the frequency of light. And to end, let me acknowledge many of my students and postdocs who have contributed to this work. And in particular, I like to acknowledge Professor Lu Qiyuan, now a professor at Shanghai Jiao Tong University, for initiating many of our theoretical work, as well as Dr. Avid Duct for initiating many of our experimental work. And let me stop here and thank you for your attention.
Yeah, thanks a lot, Shanhui, for a wonderful talk. And okay, so let me. So, do we have any questions?
So, Shani, I'll start with the question.
Yep.
So, on the last part where you have this second ring inside the first ring, are you also independently modulating the two rings, or you're only doing the electro-optic modulator on the outside ring?
Only the outside ring. Yeah,
Okay.
The inside ring is passive just to set the boundary.
Okay. And if you wanted to push this to the quantum limit, you would have to do this at the single photon level or something like that.
That is right. Yeah. So, for example, one can think of quantum walk along frequency axis, which I think actually is kind of interesting.
Yeah, yeah. So people have done that in the silicon nitride waveguides in the spatial domain, but
right.
You're thinking
in the spectral domain.
Spectral domain.
Yeah.
Interesting.
I have a question.
Yes.
So basically, it's very interesting. But is it possible to push the analogy with condensed matter even further by introducing interaction between photons?
Yes. Yeah. It's a very interesting question. So we actually have done some work, theoretical work that I'm not showing. Certainly, fiber has nonlinearity. So you can do nonlinear thing this way. The interesting aspect is that the standard nonlinearity in fiber, the Kerr nonlinearity, when you write it in the synthetic dimension, is actually long-range interaction. So it doesn't do, for example, but Bose-Haber model, where the interaction is strictly local. So I think this is, on the other hand, if you design the dispersion of the fiber in the right way, you can actually do Bose-Haber model. So I think this is something we're definitely quite interested in. If you shoot me an email, I'll be happy to send you the paper that describes some of these efforts.
Thank you.
I think Joel has an interesting question. Joel, go ahead.
Well, the question is, the concept of synthetic dimension looks like what's done in magnetic resonance imaging to create three-dimensional scans of internal organs. So the question is, can your techniques be applied to medical scanning?
That's a very good thought. I don't know, but I think that the short answer is I don't know, because I really know nothing about magnetic imaging. But I do think that this kind of techniques through modulation to couple different degree of freedom together can be actually fairly general. So I'll be very interested to learn what you are saying.
Hi, I also have a question, maybe two.
Go ahead.
Thank Professor Fan for the inspiring talk. So it is possible to realize the topological physics using the like single ring resonator on chip design, like integrate form.
I think so. Yes. In fact, there are already efforts, for example, in Marco Loncar's group on using their lithium niobate on-chip ring resonator for some of the synthetic dimension experiment. So, and we are certainly thinking along similar lines as well. The fiber platform has something, I think it's very complementary, the fiber platform to the on-chip platform. One of the nice things about the fiber platform is that you can put amplifier in. So loss is less of an issue, but also means that in fact, it's more straightforward to explore many of the non-Hermitian topology things that people are getting to be very interested in. So this is in fact a direction that we are also quite interested in as well.
Thanks. I have another question. So what's the like the maximum electro-optical modulation frequency you can achieve in your experiment?
In our experiment, we use about a few gigahertz of modulation frequency. So the modulator actually has a maximum modulation frequency of a few gigahertz. Given our free spectral range is about 15 megahertz, we usually modulate only probably up to 100 megahertz or so. So we're way below what our modulator can do. I think that these days, people, especially electro-optic modulator, are pushing modulation frequency into at least a few tenths of gigahertz, or maybe I'm guessing even slowly approaching 100 gigahertz. So, so it is actually possible to modulate at pretty high frequencies in these systems.
Thanks.
Any more questions for Shanhui? So if not, let's thank Shanhui once again for a wonderful talk.
Well, thank you. It's a pleasure to visit.
Thank you,
Thanks a
Shanhui.
lot.
Hope to have you here in person next time.
Sure. Yeah, definitely. Yeah, it will be fun.
Take care.
Okay.
Yeah. Okay. Thanks so much. Bye.
All right. Bye.
Bye-bye.